Hi, I am Martijn over here, and in this video I will explain Pappos' hexagon theorem to you. This over here might be an illustration of Pappos, but he's very old, so I'm not sure. And you can imagine that his theorem is also very old. And something interesting is that this theory can only be proved in the framework of projective geometry, which was invented many centuries later. And Euclidean geometry that was invented at that time, it was not general enough to provide a proof without a lot of extra conditions. That's not a problem, but if a theorem holds under more general conditions, it's often, as in this case, a lot more elegant. Well, I'll tell you what this theorem is about. It's a very elegant theory, so all it will take is a few pictures to understand what I'm talking about. We start off with two sets of three collinear points drawn on these two lines here. There are 9 lines that connect a letter to a dashed letter, but we will not use the line from A to A dash, B to B dash, and C to C dash. That will result in this. Now we choose 3 points of intersection of these 6 lines in the figure indicated by the red A, B, and C. So that's this point, and last this point. And note that all we assumed so far is that we started with 2 sets of 3 collinear points, and from there on we started constructing, and those are not extra assumptions. And the theorem now states that these 3 red points are collinear and so are on the same line, and that's this gray line over here. Using Euclidean geometry, we can show this result using some extra conditions, but as mentioned before, this theorem holds true for any configuration of, well, 2 sets of 3 collinear points. So we could also use these 2 sets. You see I've interchanged the letters a bit, but that's allowed. All they have to be is collinear. And now if we look at the lines A to B dash and A dash to B, these lines are parallel and thus they have no point of intersection. So trying to prove that this point of intersection that doesn't even exist is collinear to 2 other points, that gets kind of tricky. For this problem there's a simple solution, using projective geometry. In that case, even parallel lines have a single point of intersection, which is exactly what we're after. I will explain how this projective geometry works here. Instead of the 2D Euclidean plane, indicated by the x and y direction here, we use an affine plane, which we call the projective plane. In this picture, it's the z equals 1 plane, indicated by a green square. We can create this projective plane by adding the third dimension, the z direction, and the plane we use for now is indeed the z equals 1 plane, and that makes it parallel to the Euclidean xy plane. As in Euclidean geometry, this is where the points and the lines are, and in projective geometry, we have a new way of defining the points. Instead of using the coordinates, we can use vectors. So think of any vector in a 3D space, for example the vector A over here. You can scale it up, make it larger, make it smaller, make it negative, anything you want. Well, those are the things you can do. And taking all the points this vector has pointed to, you will end up with a line crossing the 3D space. This is a 1D subspace, and this 1D subspace intersects our projective plane in one single point. This way we can identify the specific point in the projective plane with a specific 1D subspace, which is in turn identified by its direction in the 3D space. Now we have solved the problem of parallel lines not having a point of intersection, because there are some directions in the 3D space parallel to the projective plane. So these will not result in an intersection with the projective plane, which is the same as the Euclidean plane lifted up a little bit in this example. Still, a direction in 3D defines a point, and these points form an addition to the known Euclidean points. So, for example, the point that is defined by the direction of the x-axis, it will go all the way over there and never intersect the projective plane. So that's a new point, and this new point is used to define the intersection of parallel lines in the projective plane. Projective geometry brings us even more advantages. You can consider three directions A, B, and C. I have stopped these lines, these 1D subspaces at the intersection with projective plane. So now the ends of these thicker lines resemble the points A, B, and C in the projective plane. And 3 points actually always form a triangle, except for one special case when these 3 points are collinear. Now, there is a certain property of 3 vectors in a 3D space with a similar feature, the determinant. Remember that it's the oriented volume spanned by 3 vectors, which I tried to show over here. The intersection of this parallelepiped with the projective plane is a triangle. It's not really relevant, but I think it's a nice illustration of the relation between the two. Under one condition, the volume of this parallelepiped is 0, and that is when the 3 vectors, that A, B, and C, all lie in the same plane. Now, working with that condition, we know that A, B, and C span a single plane, and we have another plane in this 3D space, which is the projective plane. Now there are 2 options. There is a line of intersection between these 2 planes, and so by our definitions for points in the projective plane, we know that these points are on this line of intersection, and well, then we find that the points A, B, and C are collinear, which is the similarity we were looking for. The other case is when there is no intersection between the planes, and that is actually also fine because the points that are spanned or created by A, B, and C are all 3 points at infinity, and in projective geometry all points at infinity are connected by a line at infinity, which makes them still collinear. So what we have seen over here is that if 3 points are collinear, the determinant of the 3 points is equal to 0, and also the other way around.